Now, please welcome our next presenter, Mr. Makoto Inoue. それでは井上さん、よろしくお願いいたします。
Hey guys, thank you for coming to my session. My name is Makoto, and actually I was born in Osaka, so I'm very honored to be able to present in this city. And by the way, last session was very enterprising, so I wanted to make it a bit more casual. So that's me on some rainy day, and this is actually NFT, pop NFT. Some of you might have claimed in this stage as well, but I have a hobby of this doodling me and every event I go. So this is all the pop badges I made. So if this talk interests you, and if you want to talk to me more, you can have a chat with me afterward. And if you tap this card, you can get this cute NFT badges. And so let's start. So I already introduced myself as Makoto, but everybody in the Web3 space, your identity is the actual on-chain identity with your wallet address. How many people have wallet? Ethereum wallet? Okay, about 30%. Yeah, so for those of you who have never had Ethereum wallet, the wallet address looks like this, 0x5A. It's actually my Ethereum address. But most of the time, if someone wants to send me something on chain, you can't really remember. Just like you don't remember your bank address either. But ENS, Ethereum Name Service, provide human readable names so that if you go to wallets such as MetaMask, and if you type matoken.eth, which is my on-chain identity, it looks up 0x5A. So you can send me ETH or any shitcoin. And so today, just a bit so ENS is one of the oldest smart contract and the dApps running on Ethereum blockchain since May the 4th, 2017. So that's, the Star Wars May the 4th. I think we intentionally launched on that May the 4th day. So, Force とともにあらんことということで、皆さん覚えられると思うんですけど、It's been since 2017. And we have over 1.9 names owned by 100K unique addresses. And what's interesting is because blockchain is a global ledger and all the data is verifiable from anywhere if you have access to the node. So there are lots of data platform where it kind of puts all the on-chain data and you can query. So if you don't trust what I'm saying, you can actually create go to place something like a Dune. Does anyone know Dune dashboard? Yeah, 2 people. So Dune is amazing tool where all the on-chain data is kind of indexed, and you can write a query called SQL. Does anyone know SQL? SQL, yeah, it's called structured query language, and it's one of the it's programming language, but many even non-coder can, or business analysts can use to query basically data. And so you can check lots of on-chain, basically create a dashboard using Dune dashboard, and which I love it. I'm one of the early user of the Dune, but at the same time, I've recently worked with Google Cloud team to bring some of the aspect into their data platform called Google BigQuery. That's where, like Dune, you can write a SQL and to query the large data set, but they have a few added features other data analytics platform doesn't have, which is the fact that you can actually run JavaScript within SQL, and the JavaScript is one of the most widely used programming language. So everything you do, there's some sort of JavaScript library. So any logic you can't express with SQL, you can augment with JavaScript. And also because it's Google, they basically embed their own AI model called Gemini. And by using that, you can do a bit more than just doing vibe coding using copy and pasting some query into your ChatGPT and do it. So today, this topic is by using my experience of porting the data platform into this Google Cloud BigQuery, I wanted to show some of the aspect of how you could do it by yourself. And I think first and third part, you might not even need a specific kind of programming experience. So let's start. Yeah, so first, SQL prompting with BigQuery. So this is kind of their platform where they have something called blockchain, the long table name, where it's almost like an Excel spreadsheet that it has lots of column data, and it has all the information of the transaction and of your on-chain kind of interaction. And if you want to basically query, first thing you can do, even if you don't know SQL, you can say, show me the first 5 rows of this table. Interestingly, because this prompting environment is embedded into the query platform, they already kind of do some digging of the data, and they can even suggest some interesting query. So even if you don't know any SQL, you can kind of automatically generate it. But what's interesting is actually Google's big cloud environment gets charged per query, and the larger query size is, more expensive it becomes. So the first example is like, even though it says first 5 row, it says you need to read 2.61 terabyte, which is a lot. So you can say, oh, okay, I just want to know the last 1 hour. By minimizing data set, now it's shrunk to 900 meg or something like that. So you can kind of keep refining, and you can run the query. So you run the query, that's amazing, but this makes no sense. What the data, what's the topics? So if probably this usually need programming knowledge, but there's what people mostly use is some sort of decoding library. This is one of the most famous JavaScript library called Ether.js, and you decode this kind of lots of numbers into this human readable. So in this case, it was some sort of the token transfer information. So you usually need to use this JavaScript function. But most of the analytics environment where you run SQL, which I showed you earlier, this function is not available. But because BigQuery allows you to use JavaScript, create your own JavaScript custom function, our founder, Nick Johnson, wrote a blog post about actually how you use it within a BigQuery, that you can basically define create or replace function name with the location of the JavaScript library. And by embedding how to kind of call the function, you can actually use it within a BigQuery so that like, with this huge table, I actually want to extract this name register the information. And by doing that, the data looks like 0x ending 066b, but it just shows that like this is a name registration information. It's successfully decoding crypto Wordle. So that makes it more usable. And with this information, I basically go back to, I created this table. So now I want to show something more interesting. So what I try to do is, okay, so there's a guy, name called roughgod.is, and who I just met in East Tokyo. There's a rumor that this guy might be here as well, and I might have seen it just now. But what he's known for is he basically registered his name for 6,000 years, and he claimed he has a name with the longest registration period. And because the ENS name costs like $5 a year, he claimed that he paid like 45 years, which is crazy. He just said it was a performance art. So I just wanted to actually dig in. So I initially said, just did a Bible query, or can you figure out how much is he paid? And I think it's too early on. And sometimes like you need to specify. I think I need to dig in a bit by myself, but like, it's good that this SQL prompting gives a base so that I can easily fiddle with, and it was actually 21 ETH because ETH price was half of what is right now, but like this makes it a lot easier to query online. So that's kind of second chapter. And the third chapter is, so far, it's interesting, but you could, I think with this baseline setup, you can even do more interesting. In the first example, I did a kind of vibe coding prompting to generate an SQL. But what BigQuery allows you is you can actually do some sort of machine learning AI within the SQL syntax. What it means is there's one called ML understand text, and by doing that, you can say oh, I want to understand which language this certain text is, so that you can kind of find, or something I think this was the names that owner of Ralph Gold owns, and I wanted to categorize what kind of names he has, and or Biku is the most or something like that. So you can do categorization, or you can find out all these names, how many names are actually English-based or Chinese-based or Japanese-based. So you can do machine learning categorization is understand text. And also, that's kind of interesting, but you can also write a prompt as part of SQL to say, so not prompt is generating SQL, but you write prompt directly on the SQL to say, for all these names, can you suggest some different names? Is the prompt I did, and this is a output. So I did the just formatting, and then basically with the rough code, actually AI can suggest what other names are possible. And the power is that to do that, if you don't have this environment, you usually have to download all the data set, and they have to set up your own data platform, then have to run it. But you can all do this within their Google Cloud, and then you can kind of plot the chart and all the stuff. So that's quite powerful. And beyond that, there's a lot of, you can do image recognition, prediction, and recommendation. And I'm not a machine data scientist, so I also spend a couple hours using their online course Gemini in BigQuery. So I think if you use BigQuery with the Ethereum dataset, it makes a lot more achievable to use kind of interesting AI and machine learning analytics for your Web3 data. And so this environment, I'm still working on it, and it's almost done. It hasn't been announced yet, but if you follow ENS Domains X, when we announce, you will be the first one to find out how to access to these data set I decoded using the BigQuery. And that's it. Thank you very much.
Thank you very much. ありがとうございました。それでは続きましてのプレゼンターご紹介させていただきましょう。ディエゴ・キングストンさんです。We'd like to invite our next speaker, Mr. Diego Kingston. Yeah, Mr. Kingston, the floor is yours.
ありがとうございました。皆さんと一緒に、大阪にいてとても嬉しくて光栄です。Excuse me, I am now going to give the presentation in English, but I hope that sometime I will be able to do it in Japanese. So my talk is going to be about the future of CKVMs, and especially about post-quantum signatures in Ethereum, which is one of the current threats we are facing. And so I wanted to talk a little bit about some design choices or trade-offs and some of the recent developments that we have seen. So this is a bit the outline of my talk. I am going to first mention some of last year's advances, then comment a little bit on the quantum threat, why this is important for Ethereum, then a little bit about the different signature candidates, also then talk a little bit about these multilinear versus univariate Starks. So these last few years, there was a discussion between using like snarks or Starks. It now seems that this discussion is settled. And then we have to choose maybe which is the right way to encode them with polynomials. Maybe we can have both. And then some design choices, and finally a little bit about why build a different VM, especially for what is signature aggregation, what advantages this can give us. And I'll finish with a short summary of what we have been talking. So some of last year's advances. First, we saw that we have like very powerful, transparent validity proofs, that is, proof systems that don't rely on a trusted setup such as GROT16 or KCG Plonk, okay? And this has like several advantages, and we don't have this point of failure. So this is something interesting. Then we saw that we have general purpose CKVM that allow us to prove code written in Rust. And these have become like really powerful. In fact, it's been shown that we can prove over 200,000 Poseidon 2 hashes per second, or even more. That depends on your hardware, but this shows that we can prove enough hashes for what is practically meaningful for Ethereum. Then we saw the emergence of real-time proving. Right now, I think we have 3 or 4 CKVMs that can do this, and we can expect that they will get better and better. Besides, power consumption has been going consistently down, and so perhaps it will be possible for us to prove things directly from home and not from a GPU farm. There has been a lot of developments related to hardware acceleration. NVIDIA has also added in its library the instructions for example, Poseidon 2 and other primitives that are useful for proof systems. We have seen a lot of better new lookup arguments, especially lookup and GKR. We also have like new ways of arithmetization, and that gives us like more flexibility to describe our VM, and then we have also more precise specifications. So what about the quantum threat? The idea is that quantum computers have an efficient algorithm that allows us to break the cryptographic problem that elliptic curves rely on, which is the discrete log, okay? And basically, this breaks all the cryptography, easy cryptography that Ethereum uses, particularly BLS signatures, which are used in the consensus. And this is something that is very unfortunate because these signatures are really powerful because we have very fast aggregation, and the verification is rather efficient, and besides, these signatures are very small, so it's very easy to communicate them between the peers. So this also breaks all the elliptic curve-based snarks, for example, GROT16, which is, again, the proofs are very small, and so we will have to handle like larger proofs. On the other hand, the security of hash functions is reduced, okay, but this is not as catastrophic as the case of elliptic curves, and we can always restore these by working with larger digests. That is to say, if we double the digest, we get back to the security level we had. So why is this important for Ethereum? First, because if this appears, then this can break completely a great part of the cryptography we're working on. But even though this could never happen, I think it's always good to have Ethereum working with cryptography that is as robust as possible, because that makes us resilient against any kind of threats. Besides, we know that Ethereum has already accepted ZK as the best strategy for scaling Ethereum. ZK is really cheap and fast right now. So it doesn't make sense to have optimistic rollups because the cost of adding ZK is negligible. And besides, having ZK greatly simplifies the whole protocol because we can essentially verify just these proofs and then just update the results because we know they are correct, okay? So the execution is basically offloaded. So the thing is, they are going to break our signatures, and so we have to replace them for something else. So there are a couple of things we would like to have. First, of course, we want them to be post-quantum secure. Then we want as minimal and as robust security assumptions. So for example, hash functions are among the best known cryptographic primitives, so they are a natural candidate. There are other primitives that could also be candidates, but maybe they have like weaker security assumptions, or stronger in this case. Then we would like to have like fast proving, because that way we can use CK to bundle and prove lots of things. We want small proof sizes because that way we can communicate them in the consensus very easily. We would also like the proving to be done in consumer-grade devices because that increases the decentralization, and especially we would like no trusted setups and no need to update the keys during lifetime. So there are a couple of post-quantum signature candidates. We have XMSS, which is hash-based, but this is a stateful signature scheme. Then we have Falcon, for example, that works over lattices. Crystal dilithium also works over lattices. That is, for example, something that FHE uses. And also Sphinx, which is also hash-based but stateless. So the idea is that these signatures aren't aggregatable, but what we can do is use ZK to take a bunch of signatures and generate a proof that we verify them. And then just by verifying that proof, it is as if we had verified all the signatures. Okay, and that way we can aggregate. The only problem is that, okay, this solves the problem partially, but doesn't have this nice property that the VLS signature aggregation had, which was insensitive to the order of the signatures. So basically an idea of how XMSS works, because this could be the best candidate. This is because it's based on hash functions, and we know that we can prove hashes with VMs really fast. So the idea is that the signer has a long sequence of one-time public keys, and he builds a Merkle tree with that. And in order to sign, he's going to use one secret key and show the public key is contained in the Merkle tree. So we give like the public key and an authentication path. Each public key is related to a secret key by performing a number of hashes. And the idea is we are going to encode the message using something called incomparable encodings. Then each chunk is going to be interpreted as a number, and that is the number of times we will have to hash the secret key. Okay, and then the idea is that the verifier can check that this is correct by hashing the remaining number of times until he gets to the public key. Of course, when we are doing aggregation and everything, we have to be careful about using the hash function for signing and then for simulating the random oracle. If you want, you can check this paper that explains like all the implementation and all the subtleties. It's really interesting. So now we have to see, okay, we're going to aggregate using these Starks. And so we have like basically two flavors. In one case, we use ordinary polynomials. The idea is that in general, this is what, for example, SP1, RISC-0, ZISC were using or are using. But basically, the idea is we want to prove that the computation is correct, and this is reduced to a claim about certain polynomial equations that have to be enforced over some table. In this case, we have certain freedom to choose the finite field where we are going to work on, but we need it to be something called FFT friendly. And then the idea is basically we get each column of this trace table, we interpolate it using the FFT, we commit to each of these columns, and then basically what we do is we plug in these polynomials inside the constraints that we want to enforce, and then what we do is we divide by a polynomial saying where the constraints should be enforced. Okay, and to show that the constraints are then enforced, we do a low degree testing, okay, and this is the case of Fry, and we generate a proof containing several Merkle trees and everything. So this is a very fast and efficient construction, but in general, this tends to yield larger proof sizes because we have to interpolate each column separately, and we would like perhaps something a bit more efficient. On the other hand, multilinear Starks in general offer more chances for efficient arithmetizations. For example, there are ones using R1CS, but also AIR, which is one of the candidates for a special VM, or M3. So you have like a lot more freedom. We also have a bit more freedom regarding the finite field. The idea is here we use multivariable polynomials, and what we do is we get all the trace and we interpolate it just as one polynomial, not every column. And then the idea is we are going to use this efficient sum check protocol to show that the constraints are enforced. And essentially what the sum check does is transforms this claim to an evaluation of this polynomial at a random point. Okay, and then what we can do is use a PCS to show that the evaluation is correct. Okay, this is a standard technique corresponding to what's called the BCS compiler. So it's interesting that we can use two techniques combined to yield very fast provers and at the same time small proof sizes. Spartan is particularly efficient. So in general, what we want to prove is something like the product of a matrix times a vector is equal to something. And so the idea is you can split it as a claim over some random linear combination over the columns, and then this random linear combination over the rows, and this is particularly efficient. Then WIR is a bit more efficient than Fry because it works over a variant of Reed-Solomon codes that are constrained, and so the idea is that we impose over the witness some conditions. And the idea is that WIR again uses a partial sum check and then does some folding and reduces all the claims. And this way, we get smaller proofs than in the case of univariate Starks. Something that they released a few days ago was also BNew64, that is using a different polynomial commitment scheme, but has been used to prove aggregation of XMSS signatures, and it shows to be very efficient even in CPU. So it's interesting that we have a lot of research and implementations relying on different primitives. So if I had to sum up some of the differences between multilinear and univariate, in general, multilinear have gotten like way popular because of like some advantages. For example, in the case of the sum check, we don't have to calculate like inverses or anything. In general, with multilinears, we can handle better sparsity patterns, and so not have to pay for the zeros contained in the matrix. We don't need to interpolate using the FFT. And in general, because we can use where, we can have shorter proofs, and we also have like more options regarding efficient arithmetization or even the use of binary fields. As for the VMs, the idea is that, of course, we have different choices regarding the instruction set architecture, whether it's customized or RISC-V, whether we will have like one table or several tables, what finite field, koala bear, baby bear, the hash function, Ketchak, or the less battle-tested Poseidon 2, whether we are going to use circuits or lookup-based arguments. For example, in the case of Jolt, that's very easy to audit, the arithmetization, the memory argument, the PCS. The good thing is that if we do it like very modular, then we can easily switch one component for the other, where we are going to have a recursive prover or a streaming prover to keep memory bounded. But in the end, I think we will need more than just one design, especially when it comes to execution, to avoid any catastrophic bugs, because these general purpose VMs tend to have like very large and complex code bases. So why build a separate VM for signature aggregation? Well, this is going to play an important role in the consensus, and so we would like to have perhaps a simpler design that just handles the necessary logic for verifying and aggregating the signatures and ensure small proofs. It's easier to audit. It's easier perhaps to have multiple implementations in different languages. We can also have a design that can be used together with general purpose VM. So I think that it's worthwhile because we have like very tight constraints on what we would like on the signatures, and then it's easier to reason and audit and all that. So as a summary, quantum computers are here and they could break easy cryptography, so we need new primitives. We can have these by using snarks to aggregate these new signatures. And I think that multilinear snarks are a very good candidate because they handle very well sparsity patterns, and we have efficient algorithms to prove memory accesses and all that. A simple VM can be really, really helpful, especially if we want to prove in weak devices and not compromise decentralization. If you want to continue talking, I am here. Thanks a lot for your attention. Arigato gozaimashita.